Okay, so we are ready for the last talk of the morning. Luciano Luzzi Jr. from University of Trento will talk about Zoll families and systolic inequalities.
So hi, so first I want to thank you, the organizer, especially Lucas. It's a great pleasure to be here. And yesterday we saw a lot of relations between Zoll families, Zoll manifolds, and isosystolic inequality. So today I want to extend these relations to higher dimensional systems. So I want to also talk Alberto for the wonderful introduction to systems, and I'll catch up on some notations and some classical theorems. So first, let's recall the definition of a systolic ratio. So it's just so M is a closed manifold, so it's the systole divided, normalized by the volume. So just an observation here, the power is in the volume, not in the systole. So perhaps will be a root somewhere that kind of lost. And another observation is that if the manifold M is not simple connected, the Lusternik theorem guaranteed the existence of closed geodesics. So we are really not minimizing an empty set. So as Alberto explained yesterday, a core question is the existence of isosystolic inequality. So what that means, so let M be a closed manifold. The question is, can we find a constant C such that the systolic ratio is bounded by the constant C for every monometric? And subsequent questions is, suppose that your M admits an isosystolic inequality, so determine the best constant and study maximizer metrics. So some classical results when you have no trivial pi1. So at least for me, I think the first theorem of this theory of isosystolic inequality is the theorem of Lohner, when he proved that the two-dimensional torus admits isosystolic inequality, and the maximizer metric is a flat metric for a special lattice. So subsequently, theorems are Poole proved that RP2 admits isosystolic inequality, and the maximizer metric is the round metric, and of course, the seminal work of Gromov, where he proved that if M is an essential closed manifold, then M admits isosystolic inequality. And one interesting observation is that all of these theorems are based on the fact that since we have no non-trivial pi1, we can bound our systolic ratio by what I call the homotopical one systole normalized, which is the infimum of the length of all closed non-trivial loops. So this makes a difference when you are proving this kind of theorems. And okay, so what happens in the sphere case, right? So in the sphere case, Crooked proved in the 80s that we also have an isosystolic inequality. And as we saw yesterday, determine the best constant is still an open problem. So it's not known. But some observations is that it's not the round metric. So we have this existence of this Calabi-Crook metric that proves the round metric is not a maximum. So that's kind of unexpected, but okay. But still, although the round metric is very special, as proved by Balachev, the round metric is a critical point for the systolic ratio functional. And this gives power to the conjecture of Babenko and Balachev that the round metric is a local maximum for the systolic ratio functional. And this conjecture will become a theorem in 2 slides. But before, if you want to prove something like this, you have to be careful that your maximum is not strict, because we have the existence of Zoll metrics. And as we defined yesterday, a metric G on a closed manifold M is said to be Zoll if all three geodesics are closed and have the same length. And there's a wonderful theorem of Weinstein that he proved that the systolic ratio on the sphere, or more generally, it's constant along these Zoll metrics. Okay? And the theorem of Umberto and collaborators, now it's well known, they proved the Babenko-Balachev conjecture, and he proved that the round metric, it's a local maximum for the systolic ratio. So more precisely, they prove the existence of a neighborhood of the round metric in the C2 topology, such that for every metric in this neighborhood, the systolic ratio is bounded by the systolic rate of the round metric. And moreover, you can, if you have equality, the metric is Zoll. So this theorem is more or less classifying locally the Zoll metrics on the neighborhood of the round metric. Okay? And what I wanted to do today is tell you how this theorem is very similar to a theorem that exists in higher dimension for higher systems. So let me first introduce what is a higher system. Let me define. So in the 70s, Berger proposed a definition of higher system, and it goes like this. If M is a closed n-dimensional Riemann manifold, take an integer between 1 and n minus 1, and suppose that the K homology group with integers is not trivial. So we define the homological K system of the manifold M of the metric G as the infimum of the area of all non-trivial cycles in that homology class. And here, we compute the area of a piecewise smooth cycle using the Hausdorff measure. And as before, we define the normalized, because we want to compare to the volume, and this is the right power to make the normalization right. So we are normalized by the volume. So one observation here is the following. If you are looking in dimension 1, the objects that achieve your system are geodesics, right? In this context, the objects that we expect to achieve the systems are minimum manifolds, subminimum manifolds, stable, because you are minimizing in a non-trivial homology class. So in some sense, you are passing to the world of geodesics to the world of minimal manifolds, subminimum manifolds. And okay, so this is the story when we have non-trivial homology. So what happens when we have trivial homology? I will not spend a lot of time on this, so just a quick reminder. So what about higher systems homology trivial spaces? So the definition of K-system, it's much more subtle. So one could define a system perhaps as the infimum of the area of closed submanifolds, minimal submanifolds. But we encounter a very big problem is the existence, right, of this problem, because we don't have the Lusternik theorem in this setting. So this is a big problem. But although we have some interesting results, so interesting results by Lucas and Rafael, where they walk in the direction of isosystolic inequalities for the two systems in the tree-sphere. Okay, so this is just a quick reminder on non-trivial homologic spaces. So let's come back to the system on non-trivial homologic spaces, and the question is, can we find or look for isosystolic inequalities? And the answer is no. These things doesn't exist in this world. And this is a theorem by Katz and Susil. They prove that if Mg is a closed Riemannian manifold, and take K larger or equal than 2, and suppose that the homology group associated here is torsion-free, then we have systolic freedom. Okay? So some examples of this kind of manifold are the complex projective plane, the tori of manifolds that I will be interested. So to look for general isosystolic inequality in this world is to ask too much. So we have to refine our questions. So we can look for questions in the spirit of Balachev, right? So we study critical points of the normalized K-system functional. Or we can restrict the domain of the Riemannian metrics, right? So we can impose some nice symmetries on the space of metrics and try to find isosystolic inequalities there. So for instance, some nice restrictions are curvature, bounds, some symmetries, perhaps the metric will be Hermitian, and maybe you can find an isosystolic inequality there. And one example of that is the theorem of Berger in the 70s that he proved in the same paper where he introduced the system. He proved that in CPN, the Fubini-Study metric, it's a global maximum within the conformal class. So we have an isosystolic inequality within the conformal class of your manifold. And this is true for every non-trivial homology of the CPN. And moreover, this will be important, we have a rigidity statement. Equality here is attained only if and only if the metric is homototic to the Fubini-Study metric. Okay? So now I want to talk a little bit about isosystolic inequalities on CP2 and how this theory is very similar to the theorem of Alberto and collaborators. So, okay, so we have this very nice theorem by Gromov and Berger that says the following. So in CP2, for the two systoles, the only homology class that makes sense, non-trivial, the Fubini-Study metric, it's a local maximum, like the theorem on the sphere. But here, the neighborhood is in the C-infinite topology. And moreover, we have equality if and only if the metric G is almost scalar. And a quick reminder, almost scalar metric, what is an almost scalar metric? G is said almost scalar metric if it exists almost complex structure J such that J and G is almost Hermitian, so it's computable, and the associate to form is closed. So to further give the relation between this theorem and the theorem on the sphere, I have to explain to you how the equality case classify a suitable generalization of Zoll metrics in this space. And for that, I'll have to first define what I call a Zoll matrix in this setting, and then I'll give a quick proof of this theorem to show how this relation goes. So this definition is kind of long, but let's go through it. So is the definition of what's a generalized Zoll metric. So this definition is based on a paper of Lucas, Marques, and Neves, where they define Zoll metrics for generalized Zoll metrics for the sphere. So this is a generalization for a complex projective planes. So let's go. The set Z is defined as the class of almost Hermitian structure, JG, in CPN, whose admit a family, parameterized by CPN, of codimension 2 submanifold satisfying the following properties. So this family here, you have to think of this family as the family of geodesics on a Zoll metric. And we try to mimic the properties of the geodesics in this setting. So the first property of a geodesic is that it's closed, so it's a circle. So here, for every element of the family, we'll say that we'll set this element to be diffeomorphic to CP1-1, to be minimal, that's generalizing to be a geodesic, and to be J almost complex. And this is to use the complex structure of the space. Okay? And the second property is that if you look the Zoll case, there's a very large number of geodesics, right? So if you take a point and a direction, you always have a geodesic passing through this point to this direction. So the second property is mimicking that. So for every point and codimension 2 complex plane, we have one of these submanifolds of the family passing through this point with that velocity. So this is what it's saying here. And we also set that the map that takes points and planes to the space of parameters is a submersion. So this is a technical constraint. And another technical constraint is that the map that takes parameters to elements of the family is smooth in the sense of graphical convergence. Okay? So I hope that I convince you that this is a good generalization of Zoll metrics. And Also, a reminder here, or an observation, if you are familiar, if you're familiarized, or if you know the concept of J-holomorphic curves, you see that this is kind of similar to the existence of a lot of J-holomorphic curves on manifolds of dimension 4. So now let me explain how this definition enters in the proof of Gromov and Billiard theorems. So let's go to the proof. So, sure. No. In the CPN, it's exactly parameters by CPN.
I know, but I mean, saying in the sense that 2 points might be in the same CPN minus 1.
Yes, yes, in the sense, yes.
Using points in CPN to parameterize the space of CPN minus 1s, and there are too many points, right? It's a subversion, but it's over-parameterized. It's okay.
Yeah, so I think to answer your question is in the sense that, like in this sphere, we are parameterized the space of equators by RP2, because if you have this sphere, one equator is parameterized by the normal, right? So in that sense, that I'm using CPN, because if you have CPN, this is CPN minus 1. If you take the normal vector, you parameterize all the equators. Do you see? Thank you for the question. So let's go to the proof. So let AK denote the set of almost scalar metrics. So the first step of the proof, it's a normal form of the metrics around the Fubini-Study metric. So very in the spirit of the proof that Alberto gave yesterday, we have this statement. There exists a neighborhood of the Fubini-Study metric in the Riemannian matrix, and a function v of this neighborhood to the set of functions, so that for the Fubini-Study metric, this function is 1. And if you multiply this function by the metric, so if you do a conformal change on the metric G, this metric is almost scalar for every G in V. So it's a normal form around the Fubini-Study metric. And this is useful because we can use that. And now it comes the definition of Zoll metrics. So if you have an almost scalar pair, we can prove that this almost scalar pair is in the Zoll family, the generalized Zoll family. And this is basically the existence of pseudo-holomorphic curves given by Gromov. And a nice work of McKay showing that the other properties kind of enter in the definition that I gave. Now, the fourth step is to give a Weinstein theorem in this setting. Okay? So the normalized system is constant along the generalized Zoll metrics in CP2. So this is the Weinstein theorem in this setting. The fourth step is the most fun step for me, is that there exists a neighborhood G, a neighborhood W of the Fubini-Study matrix inside the almost scalar matrix, such that for every metric in this neighborhood, the Billiard theorem is still true. So this metric G bar still maximizes the normalized system within the conformal class. And the rigidity still holds. So how the theorem follows for these 5 steps? Kind of simple. Define U as the matrix G in V, such that phi of G belongs to the neighborhood W. Then if you take a metric G in U, you can see easily that the first inequality holds because of 5, because this metric maximizes in the conformal class. And the second equality holds because of the Weinstein theorem. And the equality case that characterize the Zoll metrics are achieved when we have equality in this string. And when we have equality in this string here, we can prove that this function phi is constant. So our metric is almost scalar and then Zoll. So this is how these two theorems related. So okay, So now we have all this work done in CP2, so let's go to CPN. So the first observation is that the Gromov-Berger theorem does not hold in CPN. This is the first observation, and was proven by Gromov. So what I mean, like but now we have a lot of systols to consider, so I have to be a little bit more specific. So the theorem does not hold for the normalized systole in codimension 2. So we can find some metrics that we have systole larger than the Fubini study metrics. So the systoles come from non-integral, almost complex structures. So perhaps you can ask and restrict yourself to the space of Hermitian metrics, and that's one question. But I'll be interested in restrict myself to the space of generalized Zoll metrics. So would be what I'm looking for. It's a generalization of the Weinstein theorem for CPN in this setting. You can put that way. So this is the guideline question. And I said before, I'll be interested in the codimension 2 normalized systole. Okay? And of course, you can ask yourself about all the other systoles that are non-trivial in CPN. There are a lot. So the first thing is to classify these generalized Zoll metrics, make our life easier. So let JG be almost Hermitian structure in CPN that belongs to the set Z. So if n equals to 2, the fundamental form omega j is closed to associate to this pair. So it's the case that I showed you before, is the almost scalar case. Now we are interested in the case that n is larger than 2. So when n is larger than 2, the first thing that happens that doesn't happen in dimension 2 is that if we have a lot of submanifolds that are almost complex, our complex structure has to be integral. So the first thing that we get is the almost complex structure is integral. And the second thing that we get is that our form is co-closed. In dimension 2, you can see that the co-close restriction is equivalent to the close restriction, just because 2 minus 1 is equal to 1. Right? Because these two things are equivalent. And the proof of this classification theorem is pretty easy. So take almost Hermitian manifold sigma. What you can show is that the mean curvature vector field of this submanifold is basically given by the codifferential of the associated form. So since we have a lot of minimal submanifolds in a lot of the directions, this guy has to be 0. Okay? So let me do some, introduce some notations. So, so first we fix the canonical complex structure of CPN, so the canonical complex structure of CPN, and we define the following sets of Riemannian metrics. So the Hermitian metrics, very, very known, metrics that are compatible with the complex structure. Now the set of Kähler metrics that are also very known, the sets of where the associated form is closed. And now I'm introducing this set, this set of balanced metrics that are co-closed, or the differential of the omega to the power of n minus 1 is 0. So the set, the balanced metrics was studied before, and it was not me that I introduced, so it was a well-known set. I think there's a seminal work of Mikaelson that do a very good job in studying these metrics. And very unfortunately, the balance word appeared yesterday, but there's nothing, there's no relations. But okay, so the first observation is that the Kähler metrics are included in the balanced metrics. And another observation is that the set of balanced metrics are exactly the set of Riemannian metrics that the pair J and the complex canonical structure, it's a generalized Zoll metric. So my question reduced to study the normalized systole within this metric of within the set of balanced metrics. So how the theorem goes? The theorem goes like this. So take n larger than 2. There exists an open set U containing the set of Kähler metrics inside the set of balanced metrics in this two topology that's such that for every metric G in the set U, the normalized systole is greater or equal than the Fubini study metric, the normalized system of the Fubini study metric. So the Fubini study metric here is a local minimum, not a local maximum. And the picture is like this, right? So here's the set of balanced metrics. And this guy here, where it's constant, I did not say that, but it's true. In the Kähler case, the system is constant along the Kähler matrix. This is kind of easy to see. So we have this shape. This is what happened with the normalized system in this case. So okay, so we solve kind of the problem for generalized Zoll metrics. There are Zoll metrics associated to the canonical complex structures. What about other complex structures, right? What happens? So unfortunately, I don't have an answer for that, but we can study a case where we have one parameter deformations. Okay, so it's the case of deformations. So the theorem goes like this. So fix n larger than 2 and take a one parameter deformation within the set Z of the one parameter deformation of the Fubini study metric. So what we can prove is within this one parameter deformation, the system is the normalized system of codimension 2 is growing for small times. And how the proof goes is very beautiful and kind of very interesting. First, by our classification theorem, this family is integrable, and JT is balanced, JT balance, with respect to this complex structure. So the only thing that we have to show is that this complex structure is the canonical complex structures, and this is due to the rigidity of complex structures in the complex projective plane. So there's this theorem by Kodaira that says that exists an isotopy between these complex structures and the canonical complex structures. So now, module this isotopy, these metrics JT are balanced with respect to the canonical complex structure. And we just apply our previous theorem. Okay? And I think I rushed a little bit, but okay. So this is the last slide. And I want to thank you very much for your attention.